right? Let's move on. Actually, I that's the other thing. I think I find a key on how to work from home, right? So I don't know if it's for you or not, but well, I think well to work from home you can just work as you are you have to go out. That means actually when I work from home, I still dress like I go to work, still work on the time I have to work here, and I mean, it's kind of similar. Well, create similar environment when I work here. But I know that this might not be uh, suitable for all of you, depending on the environment at home. But well, I think this is one of the tricks that uh, can be used later. Okay. So what we have seen in the previous slides are the way that we can derive the formulas of linear regression, and we can actually use those formulas in calculations. But in reality, when we implement it, we will not do that. We will not do the math part like that, but we will use the libraries which will do the optimization using the equation that we derive to calculate the parameters. Once the parameters are calculated, then we can assess the goodness of fit, right? Whether the data and the model kind of fit together or not, by looking at the parameters called the coefficient of determination. This coefficient of determination, or the R square. Right? This is number that indicate the proportion of variance. Right? Proportion of variance that is predictable by the model. So how does it work? Let's look at the picture down here. Say that we have 4 points here, the purple points, and we have the regression line in black. This is the line, the predicted value. And if we calculate the values of y and the average of y, we get the green line here. So if we take comparison between the points and the average of y, we will get the total variations of data. Now, when we say that how much the model helps in terms of reducing variation, what does that mean? It means that when we get the model, we get the black line here, and that this black line would lift the values of y from y bar here as something like you don't know author's variable, so you just know average, to this value that if you have this value of x, you should have this value of y, right? But still, there is still unexplained variations or the residual. But this red part is explainable by the model. So combining both, you get total variations, right? So the coefficient of determination would measure the percentage between explained variation and the total variation. So it means that we would just get the explained variations and divide it by the total variations and get the value of R squared. So in terms of equations, we have y in linear form, and the R squared would be the sum square yy. Sum square yy is the variation of y minus the sum square error divided by the sum square yy. So in this picture, sum square of yy would be the total variations, and sum square error is actually the black part here. So if we take the blue part minus the black part, we get the red part, and then this red part divided by the blue part, right? The sum square of y, you get the proportion of explainable variance, the red divided by the blue. Okay. For this one, we get SSYY divided by SSYY, which equal 1. And the other here get SSE, sum square error, divided by sum square YY. Right? And we get the R square. So what are the sum square YY and sum square error? Sum square YY come from the variations comparison to the mean. So it is actually the value of yi minus the mean of y and square it, and you get the sum square yy. Sum square errors comes from the summation of actual y minus the predicted y, right? Minus the predicted y, you get some square error. Okay, r square is would tells you the higher r square, the better fit. Values of r square is between 0 to 1. So if r square is large, means that x contain information about y. So that means x explain y. If you compare between two x, right, two variables, one give you better r square than the other, it means that that one have information of y more than another one. Okay, so it means that r square can be used to measure the fitness of the model and the data. All right, now from our data, let's take a look at the result. Let me switch to R. So here I would create a model. Linear regression model can be created by using LM function. LM function require the input as follows. You need to give the formula and the data. Okay, at least these two, the formula and the data. What is formula? Formula in this case would be the formula, or actually a way that you can write relationship in R. That would be a list of variables, and using tilde to indicate that you want to create a model between them. So now if we want to say create a simple linear regression between the weight and the mileage per gallon, I would write it like this: mpg as the response variable as y, and tilde. Tilde is symbol on the top left of the keyboard, right? Tilde. Some of you may use tilde as language switching. I would suggest you change it to do this, because either you write program in R or in Python, you will have to use this symbol, because in Python it means negation. In R, it means that you want to create a model of one variable that depends on another variable, WT, using this dataset, MPG. Okay, now I have the model. Right. Assign it to model and run it. Object WT not found. Why is that? Oh, sorry. MT cars, wrong one. Okay, done. And then I can look at the model summary. The model summary will give me the explanation of the model. So it gives me the distribution of the residuals. I can see that the residuals, the median residual is around almost 0, and the first and the third quartile is about here. And it gives you assessment of the model parameter as well. So it gives you that the intercept of B0 and WT and the values of B0 and WT, right? And it also gives you this p-values test, which for now I think because you haven't learned the hypothesis testing yet, right? Have you learned hypothesis testing from the statistics class yet? The t-test. Did you learn the t-test in stat class yet? Yes, no? The response, that means I'm not sure actually. Let me switch to this one. Okay, so the explanation of the coefficient of these coefficient. We have estimates. These are the values that calculate from the formula. The three values here, you can understand them if you already learned about hypothesis testing. Okay, these are the values to indicate whether these coefficients are significant or not significant, right? Whether they are significantly different from 0 or whether they are not significantly different from 0. The meaning is that whether this value can be treated as 0 or not, whether the value is high enough to be treated as not 0. Okay, and the test will be the student's t-test. Right, the student t-test would compute the t value from the estimate value here, and using together with the standard errors to compute the p value. This p value would test whether this value is more than 0, definitely, or not more than 0. If it's not more than 0, that would suggest that you should or you can remove those variables from your model. Okay, so that's the explanation. In my slide, I also contains that explanation here, but because I do not know if you have learned this from the statistics class yet, so for now, at least you get the estimate. The estimates are the values from the equations, from the formula that we have derived earlier, right? For the rest, once you learn about learn those in statistics and then you decide to work in data science, I would suggest that you try to understand them because they are very important. So when you work with client outside, they'll also ask you which variable that they can remove or not. The t value here, right, is the coefficient of that measure how large the difference between the estimate and 0. Right? And the standard errors are calculated from the data points, and we get this probability that the parameters is more than 0 or is not. If it's not, then it means that it is by chance, right? Okay, so at least now you can know the estimate, the values of the coefficient. Right, so we can estimate value of coefficient. We can estimate r square from this. The r square giving you here is 0.7528. Okay, 0.7528. So you have residuals as evaluation. We have r square as evaluation. The error, standard error here, residual error, give you the deviation from the regression line, right? So for r square, the higher r square give you the better model, but because when you increase the number of variables, r square will always increase, mostly, because you kind of give the model more information. But there's a problem there, because it is possible that the increment in performance might not worth increasing the number of input. So instead of looking at r square, there is a measurement called adjusted r square, with it adjusts the number of value of r square based on the number of parameters. Okay, so simple speaking, right? Simply speaking, in summary, would be that when you look at r square, I would suggest you look at the adjusted r square. The adjusted r square would account for the number of parameters that you use. The formula for the adjusted r square is like you kind of divide the value with the number of parameters that you use, and then multiply by the values of parameters that are significant, I think. I will find a formula for you later on, but at least the meaning is that the adjusted r square would adjust the values of the r square based on the number of parameters. Okay, and the last one is F statistics. F statistics here, F statistics, which also you need to understand about stat tests. F statistics measure variation between groups divided by variation within groups. So in this case, the variation between groups comes from the variation that you get by using the model. When you use the model, and when you use just the mean to do the work, and divided by the variance, you get the value. If this value, so in terms of comparisons, if this F statistics is more than 1, like this 90, it means that the model impact the change. That means the model can predict the trends, all right? And the value of P would be significant, would be less than 0.05. Okay, this is F statistics. Again, for the moment, I would expect you to grasp the concept, mainly the R square concept, and that should be fine. For the others, you need to learn the whole thing in the statistics first. We kind of come up with this maybe before the stat class, and that is not actually a good idea. So at least understand R square, know how R square work, know the residual. That would indicate the deviation from the mean. That's good enough at the moment. Okay, then you can make prediction. In R, prediction is done by using the function predict, and then the model that we have and the data that you want to use in prediction. It will give you an assessment of the predicted y. So these are the predicted value of the based on the simple linear regression that we create, right? MPG equal the coefficient multiplied by this coefficient minus 5.34 multiplied by x, which is WT, and plus estimate there, plus the intercept there, and we get the prediction values here out. Okay, we can do the same thing with another one, HP and displacement. And what I want to show you here is that because we know that these two contains positive relationship, what I want to show you is just this one, that in positive relationship, the displacement estimate of the parameters of displacement of the coefficient is 0.43. And also you can see that the R square is around 0.6, lower than the previous one, meaning that the previous one has higher relationship, right? But that's for the MPG, right? This is for HP. I want to show you just that this is how positive relationship look like, and this is how negative relationship look like. Sorry. This is how negative relationship look like. You get negative slope. For the positive relationship, you get positive slope. In the case of no relationship, right? In the case of no relationship, you get something like this. But in R square will be approximately 0, right? And that indicate that that's not a good model. And you can see F statistic will be less than 1, right? So these are the way that you can assess whether the model is good or not good. Okay, that's for the simple linear regression. You can increase the number of parameters to predictors to like 2 parameters, more parameters. Now the name would change from simple linear regression into multiple linear regression. The difference would be that you have more than you have more than just one terms. You have multiple terms. That means in terms of calculating the parameters, you have to do the partial derivative of each, right? And then you have the systems of equations to solve. But we are not doing it here. All right. That it can be done, and it's quite a little bit tedious. And if you want to learn more in the advanced computation, advanced computing, advanced science, I would suggest try that. But for now, we will take a look at how we can use multiple regression. Right? We, as you can see, we do the same thing, but we for here we used WT and HP to help predicting the MPG, and that can be done by using the same form. Just add plus HP here. And you can see that the parameters here will change a bit because we add another parameters. That means these parameters, the HP, would account for certain variations, and it will change the parameter here a bit. Also, you can notice that R square increased quite a lot actually, from 0.7 something to 0.8. That means it's already explained 80 something % of the variations. Okay, so this is how it works in the multiple regression. Okay, that's no. Okay, so this is when you please notice here that when I add two parameters here, I add it in the add sign, right? Add it to one another, but this would imply that I have assumptions that WT contribute to the weight, contribute to the economy of the cars, and horsepower also contribute to the saving of fuel in the cars, but they both contribute independently, right? They both contribute independent. Right? Independent means that when each parameters contribute to the model, each contributes separately and not in combination. There are not any interaction between them. But in reality, it's not like that. Sometimes the value depends on interaction between elements. Interaction, what does it mean by interaction? It means that the value would change according if one variable interact with another variable. For example, the number of infected people would increase if the number of susceptible group interacts with the number of with the group of infected people. So they have to interact for the number to increase. These are interactions. Okay, interactions occur in reality. A lot of them occur in reality, like when the outcome depends on more than just one variables. Like if we talk about the drug and alcohol level, that's why doctors suggest that you should not take drugs with alcohol, should take drug with milk, because there are certain interactions between them. Or the number of infected people, as you can see that, and all credit card types, number of active credit card usage per month. These are also interactions. Okay, so for linear regression, to include interactions into the model, this can be done by using this star sign, right? By multiply WT with HP here in the formula, you indicating that these two have to be considered as interacting term. So in the evaluation, the actual equation would be, the actual equation here would be MPG equal B0 plus B1 WT plus B2 HP plus B3 time WT time HP plus epsilon. This will be the final equation, right? The final equation will look like this one. That when you write like this one, it means that both WT and HP also contributes individually, but there will be an interaction term between them. Okay, so this is how it is represented here in R. And from this, you can see that there are in total 4 parameters: coefficient for the B0, for the B1 of the weight, B2 of HP, and B3 for the multiplication between the two, right? And you can notice that here the R square increased further. That means include interaction would explain this relationship better than not including interaction, right? So these are the way that you can create the linear regression model. Okay, from the theoretical point of view, how can you derive the parameters, to the numerical computation using R, right? And now here's your lab work. In this lab work, using the same data set, your Superstore data set, Did I have another? Let me check. I should have the set one, right? Lecture 8 demand. Oh, that's different data set. Okay. What to do? Actually, I was instructed that I should not give you too many works during this period, and I already give you hard assignment last time on the Monte Carlo, right? You got 2 weeks, so let's say there's nothing to submit next week, but you can, if you want to work on that, so this will not be the requirement for you to submit next week, but I will upload the data set for you to try on. Is the demand data set from this logistic company. I want you to create a linear regression model to predict the demand. The data set looks like this. So basically no lab this time. Okay. But I'll upload the data for you guys. Let me open the data set first. Here. Not tab, but semicolon delimited. What happened? Oh, I see. Need to move it here. Okay, and text to column. Right, this is a data set. Need to share it here. So I'll share the data here for you guys, but no lab this week. Okay, if you want to test the concept, you can try this. There is this demand and input. Okay, we have the value here, the total order, and the input, on the various parameters from different order type. You the lab here, if you want to do it, you can try that. You can create a model that would predict the daily demand, right? The total order, right? Data set contain 12 predictors, and the target is the total order for daily treatment. Okay, so that means you have, in terms of the data set, you have the target here as the output, and the remaining here are input. Okay, you can play with that for this linear regression task, and to get around to know how it works, to see the R square change, how the better model that, right? But there's nothing to submit next week. So next week, what you need to submit would be not what you need to submit for the work would be the Monte Carlo work that I gave you last week. Is that right? I gave you 2 weeks to work on that, right? So it should be that. Okay. So this is it. We have already learned the first machine learning based on the regression model, and you can see that there are lots of statistical technique that you need to know, and I can cover here just some part of that because many of the parts have to be covered by the theoretical approach in the statistics, right? So at least in this class, you can see how you can get the parameters from the linear regression equation. You can see how to evaluate the linear regression equation and use the values to use the equation to make prediction. Okay. Next lecture, we will jump from the linear regression, which predicts value, to the first classification problem, to the which is the logistic regression model. Okay, so for this time, we'll end our class here. Do you have any questions? Yes, we have one question here. From the last lab, task 3, problem 2. How can I check that whether two consecutive rows have different categories? Let me check the last lab first. Task 3, problem 2. Analyze the time of order. Analyze the distribution of order processing time. Analyze the time between order of different product categories. Right? Task 3, problem 2. How can I check that whether two consecutive rows have different category? The time between order of different product categories. You can sort them first and use group by, right? Let me share this. Suppose I have the file here. Superstore. Yes. Superstore CSV, right? And what? Row names are not allowed. Oh, sorry, I forgot. So Python. Duplicate row name. Oh, it's by pipe. Right, and then I need to load the library, tidyverse. Right, your question is how can you be sure, right, that the two consecutive rows contains have different category? How to check that? I think there's a better way to do that. Say if you have Superstore here, this is the data set, and we have order date. I'll just select the two out. Select order ID, order date, and category. Say something like this. Then I will have this data, and then arrange category. range by category and order date. So what I ask you to do is to find the size of the time between order of different product category. Oh, so it means that between time between order of different product category. That means the time between order of, for example, of furniture. You can see that this one is 0, this one is 0, this one is 1, this one is 0, this one is 1, right? So what you need to do is to calculate the diff in time between this one and the one before it, right? How to do that? This can be done by just mutate between different product category. That means copy the column order date to another column, then shift the column to make the time diff between the column might help. Yeah, just like the TA said. So that's what I'm trying to show you here, that I'm going to mutate another column that is the shift version of the order column, and then just minus it. Then you get the time between order. And to get it done, the function is order date dot one, say, and this one would be is it lag, right? For lag of order date. Here you now have the lag of order date. Then you can calculate the date diff, right? You can do that the rest yourself here. Okay, you can calculate the date diff. Diff D diff date. That's so valid. That order date diff equal. There's a function. I think I need to load the lubricate here as well. Yeah, like the TA said that. Lubricate. Oh yeah, that I did that. Thank you. Right, need to group it first. Group by category. Because if you shift without group, then it will shift across the category, and that's not the thing that you want. Just like that. Actually, if that's the case, I should remove arrange and then put it here and arrange it by order date here instead of that. And then there's a function called date diff or diff date, something like that, but I don't remember. You can take a look, or you can just maybe lubricate. Let's convert YMD DMY, and there should be the function that calculate the difference between that, but I don't remember how. Diff time. Or maybe I can just minus. Well, you can find out yourself actually. I can just actually divide minus them, maybe. No, it has to be converted first. You can try it yourself later on. This is factor. Oh, I see. It's factor. You need to convert it. You need to convert it to the. You need to convert this to date first. So I should maybe use this instead. Not sep, but should use the read delim. Done. Already date time. Order ID is not found because it doesn't use that name. You see the point, right? It's just when you use different libraries, kind of creating different pane. I mean the way that it refers to the name of the variable. Right, now we have a datetime 1, and we can calculate the datetime diff. Right, we can calculate the datetime diff. Why the office supply here? I have already grouped by. Should arrange first. Furniture. Oh, I arranged it. I arranged it by order date. I should arrange it also by categories. Right. Okay. So now you have arranged data by categories and also the order date. Shift the order date, and then you can calculate the minus. Right, you can calculate the minus between them. But there's the better way to do this than this way. I think there's a function in the Ruby date called dateDiff or something similar to that to convert this not in second. This is in second. You can try to find it out, but this is the way that you can do it to calculate the time the time between order. That's done by lag them first, group them, lag them, and then subtract, right? Okay, any other questions? What should I do in task 3 problem 4? Task 3 problem 4 is it asks you to simulate the superstore order and processing time. Okay, so what I ask you here is ask you to simulate the data from that. So the superstore order and processing time, what does that mean? It means that in each order you need to have the time between order, which you got earlier, right? You got the distribution from the question number 2, and if you remember back in 3 lectures ago, we learned about how to simulate order size using quantile and random to simulate order size. Doing that allow you to simulate order because you now simulate the time that order should come in, right? The inter-arrival time between order. That means today, should it be tomorrow? That would be 1 day, or should it be next 2 days? And or just that day. And the processing time. For the processing time, this comes from the 3rd question, which I asked you to find the distribution of the processing time. Processing time is the time it takes from receiving order until shipping order. Okay, which you can again use the quantile to sampling from that distribution. Right. So that should answer your question here about how should do in problem 4. Okay, and the 5th question asks you about the order size and the processing time, which means that you have to extract order size and compare it to the processing time. Okay, and the 6th, I asked you to ask you what would happen if order would boost on every Friday. That means you need to keep track now on the weekday, whether the day that you simulate is Friday or not. If it's Friday, you need to boost the number of order by another 50%, and then see what would happen in terms of simulation, right? How to do that? What you should do is to like maybe plot the number of demand occur that we need by times, or plot the processing time that would change if there is like the boost in 50% comparing to not boost 50%. Okay. Any other questions? This actually qualify to be something like the take home. But since if it's the exam like this one, it cannot be 2 weeks. But I mean that it's quite complicated. That's why you have 2 weeks to do the task. If no more questions, then let's meet again next week. Next week we will look at logistic regression. Okay, the first model that take on classification problems. Okay, so for today, let's stop here and take care in this situation. Take care, wash your hand, and stay safe. Bye.